You are sitting quietly by a window. A clock ticks somewhere nearby. Outside, a car moves down the street. A bird crosses the sky for just a moment before disappearing behind a building. Nothing about the scene feels unusual. And yet, imagine that another person is watching the exact same moment from a vehicle moving rapidly past you. You both see the car, you both see the bird, you both see the clock. As far as ordinary experience is concerned, there is only one reality unfolding in front of you. So naturally, you would expect that if you later compared your measurements, they would match. The distance between two events should be the same. The amount of time between them should be the same. After all, a second is a second. A meter is a meter. And an event happens at a particular place and at a particular moment. You have probably never had a reason to question any of this. Your entire life has trained you to think of space and time as two separate things. One tells you where something happened, and the other tells you when it happened. But now imagine the moving observer looking back at you. Something deeply strange happens. The two of you can watch the same sequence of events and still disagree about the measurements. Not because one of you made a mistake, not because either clock is broken, and not because your eyes are deceiving you. The disagreement comes from something far more fundamental. Motion itself changes how space and time are measured. The scene outside your window has not changed. The universe has not suddenly become chaotic, but your simple idea of reality has. And that raises a question you may never have thought to ask. If two people can witness the same events and disagree about where they happened or how much time passed, then what exactly are they agreeing on? So what exactly is the same? If two observers moving relative to one another can measure different distances and different amounts of elapsed time, you might expect physics to collapse into a collection of competing opinions. But it doesn't. They are not describing different universes. They are describing the same underlying reality from different states of motion. And this is where several familiar explanations have to be removed. It is not simply that one person's clock is defective. If you replace the clock, the effect would remain. It is not because light somehow chooses one observer and refuses to cooperate with the other. And it is not because space behaves like an ordinary elastic sheet, stretching for one person and shrinking for another. The real clue is much simpler. Think about something happening right now. A lightning strike hits a tree. That occurrence has a location, and it has a time. You can identify it by saying, in effect, where it happened and when it happened. Physicists call something like this an event. An event is not two separate things, one happening in space and another happening in time. It is one physical occurrence described using both. And that sounds almost too obvious to be important. But look closely. The moment you describe an event, you have already connected space and time without realizing it. A map tells you where something happened. A clock tells you when it happened. Normally, you treat those as completely independent pieces of information, but introduce motion between observers, and that comfortable separation begins to fail. The coordinates one observer assigns to an event do not necessarily match the coordinates assigned by another, yet both observers are still talking about the same event. That is the puzzle. And the surprising part is that the key to understanding it is not hidden inside some impossible mathematical trick. It is already sitting inside the way you understand maps, clocks, and measurements. We simply have to follow the logic far enough to see what motion forces those measurements to become. Because before we go further, we need to separate this idea from the popular version of relativity that has been repeated so many times that the actual physics has almost disappeared. You have probably heard relativity explained in a few familiar ways. Time slows down when you move fast. Everything is relative. Einstein proved that nothing is absolute. These statements are not completely wrong, but they can leave you with the wrong mental picture. Because if you only memorize that time slows down, you are left with an obvious question. Why? What physically forces a clock to behave differently? Why should motion have anything to do with the passage of time? And why should distances change too? This is where popular explanations often stop. The science is not necessarily too difficult. The problem is that the explanation frequently ends just before the mechanism becomes understandable. Special relativity begins with two remarkably simple principles. First, the laws of physics should have the same form for all inertial observers, observers moving at constant velocity relative to one another. Second, the speed of light in a vacuum is the same for all such observers, regardless of how the source or observer is moving. That second statement is the one that changes everything. Imagine you are standing still and shine a beam of light forward. You measure its speed. Now imagine another observer moving rapidly toward or away from you. According to ordinary intuition, that observer should measure a different speed just as a person on a moving train can measure the motion of something relative to the train. But light does not cooperate with that intuition. Its measured speed remains the same. So something else has to change, and that something cannot simply be a malfunctioning clock or a defective measuring stick. The measurements of space and time themselves have to transform between observers. This is why saying time slows down when you move fast is incomplete. It describes one consequence. It does not explain the deeper structure producing it. Relativity is not a collection of strange tricks invented to make clocks behave mysteriously. The effects follow from a consistency requirement. Different observers must be able to describe the same physical world while preserving the same fundamental laws. And once you follow those requirements carefully, the strange behavior of clocks and rulers stops looking arbitrary. It becomes almost unavoidable. We are not going to jump straight to the famous equations. Instead, we will build the idea from the ground up, step by step, until the mathematics has no choice but to tell us what nature is doing. And once you see relativity this way, the subject stops being a collection of strange effects and becomes a single idea. That is exactly the kind of idea this channel is built to explore. If you enjoy science explained this way, without turning every difficult idea into a slogan, and without burying the important mechanism beneath complicated language, then you may want to stay with this one. Because relativity becomes much less mysterious when you stop treating it as something you simply have to believe. You can actually follow the reasoning. You can see why each step leads to the next. And eventually, the strange results, moving clocks, changing distances, and the connection between space and time stop looking like isolated curiosities. They become consequences of one simple physical requirement. That is the kind of explanation we are going to build here. Not just what nature does, but why it has to do it. So now, let's return to the beginning of the puzzle. What happens to our measurements when two observers are moving relative to one another? Because the answer begins with something both observers believe they understand perfectly: the speed of light. Now we can finally build the mechanism. Start with something almost embarrassingly simple: an event. A lightning flash occurs. A detector clicks. A spacecraft sends a signal. To completely identify that event, you need to know where it happened and when it happened. Where means position, 3 spatial coordinates, x, y, and z. When means time, t. So physics already gives every event 4 coordinates, 3 describing position and 1 describing time. Nothing strange has happened yet. The trouble begins when two observers are moving relative to one another. Imagine a spacecraft containing a light clock. 2 mirrors face each other, and a pulse of light bounces between them. For an observer traveling alongside the clock, the light simply moves straight up and down. Now imagine an observer watching that same spacecraft fly past. From this observer's perspective, the mirrors are moving sideways while the light travels between them. So the light no longer follows a vertical path. It follows a diagonal path, and that path is longer. Here is where nature creates the puzzle. The speed of light in vacuum is exactly 299,792,458 meters per second. And special relativity says that every inertial observer measures that same speed for light. So the stationary observer sees the light travel a shorter path. The moving observer sees it travel a longer path. Yet both must measure the same speed. There is only one way for those facts to coexist. Their measurements of distance and time cannot remain identical. Remember the basic relationship: speed equals distance divided by time. If one observer measures a longer distance while both observers measure the same light speed, the corresponding time measurement cannot remain universally fixed. This is the beginning of time dilation. But there is an important detail that popular explanations often miss. A traveler moving at high speed does not look down at their own wristwatch and see it running strangely slowly. Their local clock behaves normally. Their heartbeat feels normal. Their thoughts feel normal. Their second still feels like a second. The difference appears when measurements from different frames are compared, and the effect becomes dramatic as velocity approaches the speed of light. At 0.5 c, relativistic effects are already measurable, although still modest. At 0.9 c, the Lorentz factor is about 2.29. At 0.99 c, it rises to about 7.09, and at 0.999 c, it reaches roughly 22.37. That means the relationship between measurements becomes increasingly different as the relative speed approaches light speed. But now we encounter an even deeper problem. What if only time changed? Suppose we allowed clocks to disagree while insisting that space remained completely independent and absolute. The geometry of the light beam would no longer work consistently for every inertial observer. something has to happen to spatial measurements too. This leads to length contraction. Again, do not imagine a moving traveler watching their own ruler mysteriously collapse. Locally, the ruler is perfectly normal. Instead, observers in different inertial frames can assign different lengths to the same object when it is moving relative to them. And now, something important should become visible. Time dilation and length contraction are not two unrelated tricks. They are two aspects of the same underlying transformation. The mathematical machinery describing that transformation is called the Lorentz transformation, and this is where relativity stops being a collection of strange effects and becomes one coherent structure. In classical physics, you could imagine space existing on its own while a universal clock ticks identically everywhere. Space was space. Time was time. But the Lorentz transformation does something radically different. It mixes them. The new spatial coordinate depends not only on the old spatial coordinate, but also on time. And the new time coordinate depends not only on the old time, but also on position. In other words, x depends partly on t, and t depends partly on x. Space and time are no longer completely independent quantities that every observer can separate in exactly the same way. They transform together. This is the idea that leads naturally to spacetime. In 1908, mathematician Hermann Minkowski gave this structure a powerful geometric interpretation. Instead of imagining three-dimensional space evolving through one universal time, imagine physical events as points within a four-dimensional space-time. You can picture a lightning strike as one point, a spacecraft signal as another, a detector click as another. The events themselves are physical occurrences, but different observers moving relative to one another can organize the coordinates of those events differently. One observer's division between space and time will not be identical to another observer's division. It is somewhat like looking at the same geometric object from different angles. The object has not changed. Your coordinate description has. But relativity gives us something even deeper than the individual coordinates. Suppose two events are separated by a time difference delta t and a spatial difference delta x. Observers may disagree about those two quantities separately. One may measure more elapsed time, another may measure less. One may measure a different spatial separation, but there is a combination that remains invariant. Delta s squared equals c squared, delta t squared minus delta x squared. This is the spacetime interval. You do not need to calculate it to understand its importance. The key idea is this. Observers do not have to agree on every individual measurement. They have to agree on the deeper structure connecting those measurements. And that is the conceptual payoff. Space and time are not two completely separate substances that happen to coexist. They are different aspects of a single geometric structure. Motion changes how an observer divides that structure into spatial and temporal measurements, while the underlying spacetime interval remains invariant. And this is not merely philosophical language. Relativity has to be taken into account in real technology. Consider GPS. Satellites carry extremely precise clocks, and those clocks do not experience exactly the same relativistic conditions as clocks on Earth's surface. Their motion produces special relativistic effects, while differences in gravitational potential produce general relativistic effects. Both have to be corrected. Without those relativistic corrections, GPS positioning would accumulate errors far too quickly for the system to provide the precision we expect from modern navigation. So the strange behavior of time is not confined to thought experiments involving spaceships and nearly impossible speeds. Relativity quietly operates inside technology you may use every day. And notice what we have discovered. We started with something ordinary, an event happening somewhere at some time. Then light forced different observers to agree on the same speed. That forced their measurements of time to differ. Consistency then required spatial measurements to change as well. The Lorentz transformation connected those changes, and Minkowski's picture revealed the deeper structure beneath them, spacetime. The clock did not suddenly become strange. The universe was never organized around the separate concepts of absolute space and absolute time that our everyday intuition suggests. Our everyday clocks simply hide the structure, and this is where the common picture of reality begins to fail, because most of us were taught to imagine space as one thing and time as another. There is a mental picture of the universe that almost everyone carries around without ever consciously choosing it. Imagine reality as a gigantic three-dimensional stage. Everything has a location on that stage, and somewhere above it all, imagine one enormous clock ticking away. 1 second passes, then another, And no matter where you are, on Earth, inside a train, or on the other side of the universe, that same universal clock is supposedly keeping time for everyone. It feels completely reasonable. In fact, for ordinary life, it works remarkably well. If you walk across a room, you do not need relativistic corrections. If you drive down a highway, the difference between your clock and someone else's is far too small to notice. Even an airplane traveling hundreds of kilometers per hour produces effects so tiny that your everyday intuition remains almost perfectly reliable, and that is precisely why the old picture is so convincing. Newtonian physics is not useless. It is an extraordinarily accurate approximation under ordinary conditions. The problem begins when we mistake an excellent approximation for the fundamental structure of reality. Increase the relative velocity enough, and the universal clock begins to disappear. Observers can measure different elapsed times. They can assign different lengths to moving objects. And then comes the consequence that feels almost impossible. They can disagree about whether two distant events happened at the same time. This is called the relativity of simultaneity. Imagine a long train moving rapidly along a track. Lightning strikes the front of the train and the rear at precisely the same moment, according to an observer standing on the platform, positioned midway between the two locations. The light from both strikes travels toward the observer. Because the observer is centered between the 2 points, the flashes arrive together. Now consider an observer sitting inside the moving train, also positioned between the two locations at the relevant moment. That observer is moving toward the light coming from the front of the train and away from the light coming from the rear. Because light travels at the same speed in both directions, the moving observer does not assign the same simultaneity relationship to the two lightning strikes. The observer on the platform can say, "They happened at the same time." The observer on the train can say, "They did not happen at the same time." And neither observer has made a measurement error. The lightning did not change. The strikes did not move. Nothing about the distant events themselves was altered by someone's opinion. What changed was the observer's division of spacetime into space and time. This is the part our everyday intuition has difficulty accepting because our entire biological experience happens at relatively low velocities. We grow up surrounded by situations where one shared now is an excellent approximation. So our brains naturally treat it as fundamental, but relativity tells us something more subtle. Your intuition is not wrong. It is simply calibrated for the environment in which humans normally live. The universe does not need one universal present stretching across all of space. Different observers can have different definitions of which distant events are simultaneous, while still agreeing on the underlying physical laws. That is not philosophical wordplay. It is a measurable consequence of the Lorentz transformation. And once you understand that, an even more interesting question appears. If our intuition is not wrong for ordinary life, but incomplete for the universe, where did the idea of universal time come from in the first place? Now you have enough of the physics to change the way you picture relativity, and you can practice that without solving a single equation. Think of it as a simple mental protocol. Step 1, think in events. Instead of asking only, "Where is it?" or "When did it happen?" ask a more complete question. Where and when did the event occur? A flash of light, a spacecraft signal, a detector click, each is one event with both spatial and temporal coordinates. Step 2, add motion. Now imagine a second observer moving relative to the first. Watch the same sequence of events from both perspectives. Ask yourself, what does each observer measure for the distances? What do they measure for the elapsed times? Which events do they consider simultaneous? Step 3, stop expecting universal space and time. Do not immediately search for which observer has the real clock or the correct ruler. In special relativity, different inertial observers can legitimately assign different spatial distances, elapsed times, and simultaneity relationships to events. Step 4. Look for the invariant. Instead of asking which observer is right, ask, what do both observers agree on? The conceptual answer is the spacetime interval, the deeper relationship connecting their different measurements. Here is a simple exercise. Take about 2 minutes and imagine a pulse of light bouncing between two mirrors while another observer moves past the setup. Do not calculate anything, just visualize the chain. Same light to different observer, to different space and time measurements, to same underlying space-time relationship. Repeat that picture a few times. It is often more useful than memorizing the phrase time dilation because you are now visualizing the mechanism behind it. And one scientific clarification is important. This is a conceptual physics explanation, not a claim that you can personally feel relativistic time dilation during ordinary daily life. At everyday human speeds, these effects are generally far too small to notice directly. But the mental model is still worth having. Because once you begin thinking in events, observers, coordinates, and invariants, relativity stops sounding like a collection of paradoxes. It starts looking like a consistent description of reality. Now go back to that ordinary moment where we began, with you sitting quietly, watching the clock and assuming everyone shares the same present. The clock is still ticking. The room looks exactly the same. The world outside your window has not changed. But now, when you hear that familiar ticking, you know it is not the sound of some universal cosmic stopwatch keeping identical time for everyone, everywhere. It is a local measurement of time, one coordinate in a deeper four-dimensional structure. Every morning you wake up. Every evening you watch a clock. And every time you are measuring something real, but not necessarily something universal. The clock hasn't changed. What changed is the question you now know to ask about it. The goal was never to make reality seem strange, simply for the sake of being strange. It was to show how one simple physical principle can completely change the meaning of ideas you use every day: time, distance, motion, and even the word now. If you appreciate science explained through the mechanism rather than the slogan, stay with us. Because relativity does not end with the realization that space and time are connected. It opens the door to deeper questions about light, gravity, motion, and the structure of the universe itself. And some of those questions are hiding in plain sight.